interrupt your breakfast in case you guys want to laugh. So pretty much our theme is going to be frontiers of temporal and spatial physics. And our research question is, how can the exploration of mathematics and physics help us understand and explain the dimensions of time travel? Okay, so we're going to start off with a quote by Dr. Michio. So, yeah, you guys got this, all right. Smart kids. So, once confined to fantasy and science fiction, time travel is now simply an engineering problem. Okay, so now that we know this is plausible, what changes can we make in our world to make this possible? Okay, so here's a simple question. What good is basic physics? Now, it's everything, really. When you think about it, basic physics is what's made the impossible possible. I mean, think of all the amazing mathematicians and scientists we have in this country and everything that they've been doing. So how do we inspire future generations to make fantasy into fact? And that's what we're focusing on right now. We're going to do that by, let me just, over here.
With a STEM Awareness Week. When we say STEM, we mean science, technology, engineering, and mathematics. In this theoretical week we would hold it at a college and have it open to the public, especially to high schoolers. We'll put on 3 different seminars with the help from fellow Phi Theta Kappa members, both in our chapter and our region, and with the help of our math and science professors. In each of these seminars, we will focus on how time zones, GPS, and popular culture are affected and shaped by physics. Now let's start with time zones and time travel.
So for day 1 of our seminar series, we will be discussing time zones. Is it really tomorrow in Tokyo? Understanding time zones is an important but challenging concept for many students. The need for standard time zone emerged with the spread of high-speed transportation systems, first trains, and later airplanes. According to the National Geographic in 1884, delegates from 27 countries met in Washington, D.C. at the Meridian Conference and agreed on a system of time zones that is essentially the one that we still use today. Time zones are based on the fact that Earth moves through 15 degrees of longitude each hour. Therefore, there are 24 standard time zones.
On the second day, we will deal with relativity. As the great astrophysicist Neil deGrasse Tyson put it, the theories of relativity can be broken down into 2 basic parts. First, time. The speed at which light travels is the same to all observers. Second, the laws of physics are the same as measured by all observers. Got it?
Yeah.
Good. Alright, so then let's talk about Einstein's daydream. Well, he's Albert Einstein, so it's called a thought experiment. It's called the twin paradox. We take 2 twins. Let's call them the spaceman and the Earthman. Guess which one's which? The spaceman gets into his rocket and he blasts off into
Space.
the Earthman. He stays on
Earth.
The spaceman's rocket travels at 99.9% the speed of light. On a round-trip journey, he returns to Earth, and he's shocked to discover that the Earthman, his twin, is 110 years older. But from the spaceman's perspective, he's only been gone for 5 years. The time relative to the spaceman has slowed relative to the Earthman. You see, this is something called time dilation. The faster you move, the slower time progresses. Now, a lot of you probably don't see how this is like an everyday thing that we have to deal with, but this isn't an abstract concept. This is something that global positioning satellites have to deal with every second.
Since Joe discussed about satellite and space, does anyone know what's the magic behind GPS? Raise your hand. What is it? So basically, see, first the tracking stations use radio to determine the orbits of GPS satellites, and then secondly, it goes to the satellite, and then it bounces off, and goes back to the satellite, and then at last it comes, the GPS receiver computes a location at a time.
Okay, so now you've heard a little bit about the theory of relativity. So let's look at it and how it affects things we see in popular culture. So this would be what the third day of our seminar would be dedicated to. Of course, you guys have seen this, you know what it is, it's Doctor Who. Right? Is it popular? Like, raise your hand if you don't watch Doctor Who. If you do not watch Doctor Who, okay, you're like me. Okay, anyway, let's apply this and let's see. Dr. Cuckoo, not Dr. Okay. Dr. Cuckoo, he's pretty famous now, right? He's like irrigation. Okay. He says that technology in this show is centuries or maybe just even millennia more advanced than ours. But he's implying that at some point we're going to attain it. And that means what? We're going to be able to time travel. So as the TARDIS tumbles through this tunnel-looking type thing, it's actually representing a wormhole. So think about it almost with math terms. A linear is a line, right? So if we travel through time in a linear motion, it's two events. But if we distort time, if we turn it into a U shape, we're getting two events closer together. What connects those two events? A wormhole. So right now it's just about using physics to help us understand how we can do it and how we can build that time chain. So I'm going to end with this quote, which is no matter how fantastic these ideas are, we measure them in the laboratory. This is not science fiction. This is science fact. So get used to it. Now, we mentioned, right, that this morning we sort of asked you guys a quick question at breakfast. How often do you time travel? Now that you know a little more about the physics of it, would you say that you time travel never? Would you say that you time travel sometimes? Yeah. Would you say that you time travel always? Yeah. So our always numbers have slightly increased, which means we've already seen our action, we've already seen our impact in you guys. Okay? And I just want to thank this wonderful team. In all honesty, physics, like when I read the honors and action packet, physics was the one that I was like, no. I'm not, no. Just because I felt like I didn't have the mental capacity for it. So we're just going to pass the mic around and just introduce ourselves real quick. And of course, a big thank you out to our advisor, okay, who always kept us on track, made sure we were paying attention. So I'm Maria Valladares. I am from Cuyahoga in Burlington County.
Angie Gonzalez from Essex County College.
Okay. Sheila Zagara, Iota Xi.
Molly Ryan from Harrisburg Area Community College, or HAC, from Pennsylvania.
Riley Thompson, Rowan College, Gloucester County.
Joseph Hudson, thank you very much for Star Wars. From UDC.
Caroline Steele from Rome College in Gloucester County. Callie Oliver from Community College, Allegheny County South Campus. Taylor Kearns, Hagerstown Community College, Hagerstown, Maryland.
Shabam from Iota Xi. It was physics, and I don't think a lot of people are fan of it, so I would like to thank our advisor, Professor Lin.